真的吗？你在，好了吗？声音怎么测嘛？你听一下。喂喂喂喂喂喂。
因为我把那个声音调得很大，这个声音这个地方设置，然后最下面有个什么部分？
高级音频。
对，然后这里有一个我调成了1+2，正常的话，如果是人待在实验室的话，就要调成100就行了。但是因为他没有待在实验室，或者这个地方声音很小，就调成1+2。这个话就是那个之后的，还有一个问题。
你说你先说，上一句话讲的啥？
说话呀。这有个说话啊。
我知道。
然后还有一个是谁？然后这个地方。这个东西。就这个会议档。
咋了？
点一下，这里有个已开始和未开始。已开始就是小程序它就可以看了。就是开始和结束的时候需要点一下。就是结束的时候点一下未开始就可以了。以及这个网页打的这个表格就可以了。如果找不到就是这个东西。
你再点一下那个什么？
这个东西爬出来的首页就是这个，来这里又看你的直播。你不要随便帮啊，看一个题目。点一下。未开始已开始。点完了之后提交就可以了。未开始已开始懂吧？
我每次都要弄这个吧。
开始的时候点个已开始，结束的时候点个已未开始。
这个事情你教给我。
这个事情不难呀，直接就变就完了。中午的时候电脑就可以关。
反正中午的时候我就点一下结束，是吧？
对。然后这个配乐就是大门的钥匙。
等一下，中午的时候我要把这两个也关掉是吗？
对。这是大门的钥匙。中午就是测的时候关的。
中午东西我都放这了。
那个电源呢？电源开着吗？这就是电源。
还要关？我不会关，交给你。还没跟我说。确定吗？就不能马上要搞的事情搞好了，这个可以等开会的时候知道吗？
然后你中午他那个他开始他 I just want to see that I've got videos. I want to check and see if they're going to play. Can you use this one? Let's use this one. For both. Because I just want to check now that the video is going to play. Oh, no, we don't need music, it's fine. Just yeah. Yeah, no, that's not happening. Well, we can take this one out.
Like a baby. Like a baby. That's not the goal. Right, good morning everybody, and thank you very much for coming out. That was a nice summer's day, sun shining outside. So we've got now, today is the third day of the workshop. We finished it today. We've got 3 talks. I'm going to talk about the relationship between particle shape and entrainment. This is not such a long presentation. And for those of you who were here yesterday, when I spoke about the importance of integrating comminution and flotation, this continues that theme. Then Belinda is going to talk about froth. And Belinda's done a lot of research on froth and the behavior of froth. And Belinda is a great authority on froth, and as you know, we talk about froth flotation. So the whole key, the heart of flotation is the froth phase. So Belinda's going to talk about that. Then I'm going to finish up with the third lecture on electrochemistry. Electrochemical reactions in the mill, electrochemical reactions in the flotation process, and the importance of electrochemistry. We could have a whole 3-day workshop on electrochemistry, but I'm just going to keep it brief. So today is the end of the workshop, and thank you very much to especially Dr. Wang and her great colleague who did a fantastic job yesterday translating entropy and enthalpy and need to be immersion. That was really good. Thank you very much. Okay. So, in flotation, particles are recovered in 2 different ways. By true flotation, we add a reagent to make the particle hydrophobic. We spoke about that yesterday. And by entrainment, which means whether you like it or not, the particle is entrained. And this goes back also to yesterday when we spoke about comminution. Fine particles are a big problem because fine particles just get carried up with the momentum of the air coming through the pulp and they get entrained. So managing gangue, which is what I talked on the very first day, becomes very important for fine particles. And how we manage entrainment is a very important challenge in flotation. So particle shape can influence recovery by flotation. I showed you that fantastic picture yesterday of the gold particles. I think I've got it again today. Showing you in true flotation, shape is important. In true flotation, particles that are shaped like coins are easy to recover. Particles that are shaped like footballs, soccer balls, golf balls, they are very difficult to recover because the absorption of the reagent on those particles is much more complicated. And then there's been a lot of work done by our good friends, Stephen Neethling and Jan Cyril, both of whom come from the University of Cape Town. Now they are at the Imperial College in London. They've done a lot of work on modeling entrainment. So if you want to, we could say we are building on that work. And then finally, a former student of ours, Tepan Kontu, he did a lot of work showing that different particle shapes result from different milling procedures. I spoke about that yesterday. The way that we operate milling will affect the particle shape. Different types of mills will result in different breakage mechanisms. Just remember again, if I've got a particle where I slowly, imagine I've got sandpaper, and I slowly take sandpaper and I rub the particle, that's called abrasion. The particle is smaller and smaller, but it's going to be round. If I take a hammer and I hit the particle, it's going to break up into all different shapes. So the way the particles are broken in the mill will affect the shape.
首先就是讲这个浮选过程中这个颗粒上来，一般通过2种途径，一种是分子选，一种是通过夹带上来。 另外就是这个前面昨天讲的就是说在生成过程中这个颗粒的形状它是影响这个复检的结果的，比如说这个针状的或者棒状的点比这个圆形的就更容易在复检中回收的。另外是说这个关于这个夹带的模型也有一些研究，比如说是夹带跟分散或者复选处理，还有对夹带对这种颗粒带导致夹带影响方面的模型。最后就是说这个我们说的这种颗粒的这种情况，其实是还是从上游过来的，就是说上面模放的模基或者是模放的这种方式不一样，会得到这种矿物颗粒的形状就不一样。比如说你用一个搅拌膜或者是什么在滚筒里面，它就更容易得到这种球形或者圆形的颗粒，而比如说用锤子或者是用其他方式，可能你得到的这种颗粒的形状会不一样。
Right. So, as I say here, almost all processes in the mineral processing circuit are affected by shape. Classification of screen hypercyclones and thickeners. You know what a screen is? Like when you're screening or sieving, or you've got little squares in the sieve, and the particles that are elongated will fall through easily. But if they go to the sieve like that, they fall through. If they hit the sieve like that, they don't fall through. So the shape of the particle will affect that.
Cyclone. When particles come into a cyclone, the light particles go out at the top and the heavy particles go out at the bottom. But we have shown, in fact, a group in Japan, that was very nice work, I think I've read that properly, that in a cyclone, heavy particles that are shaped like this, they go out at the top, heavy particles, and light particles that are round go out at the bottom. That's crazy. That's not how a cyclone should work. For a cyclone, the fine particles go out the top, the heavy particles go into the underflow. But it has been shown that the shape of the particles, if you've got a heavy particle shaped like this, it can go out at the top. So in cyclones, hydrocyclones, in screens, in thickeners, the shape of the particle can affect the performance of that particular unit. And so we also have shown, and yesterday I showed it, that rheology is strongly affected by shape. I showed a graph yesterday where we plotted the viscosity against shape, well, against phase volume. So in other words, the number of particles in the pulp, the density, pulp density if you like. And we showed that particles which are shaped like needles, their viscosity becomes very high at a low phase volume. Particles that are round, so you can use viscosity, you can use a viscometer in your laboratory to distinguish the shape of particles. If you want to look at the particles you are using in your flotation cell, take the feed and put it into a viscometer. It comes back to what I said yesterday. When you are doing flotation research, make sure that you know the characteristic of the particles, their shape, their particle size, their liberation, because all of that will affect the flotation irrespective of reagents. And that is one of the take-home messages I'm trying to get across. When you do flotation research, you must know the characteristics of the particles in the flotation cell. So, let me stop there for the moment. Let me stop there, Dr. Wayne.
这里就是讲的颗粒的这种形状对其实是对很多这个选矿过程都会有影响，比如说这个拆分、学分分流，还有就是后面的浓缩，另外它还会影响浮水的结果，还有就是矿浆的流变性，还有就是这个仪器的磨损率什么都会有影响。比如说这个讲这个学分分流的时候，大家都知道，一般是重的颗粒在下面，然后是轻的这种小的颗粒在上面。但如果说两个颗粒是相同大小的，或者相同重量的，通常这个针状的或者棒状的一般会在上面。 球形状或圆形状，反而在悬浮分流的下层。然后Professor O'Connor 就强调这个就是你做复选的时候，这几个参数是非常重要的，一个是解离度，还有一个就是颗粒的情况，还有就是颗粒的大小或者是粒径分布，对复选都会有一个非常重要的影响。
Right, now there are many papers in the literature where people are trying to quantify shape and determine how comminution processes and mineralogy affect shape and how shape in turn affects unit operations. Now, what we mean by this is that gone, no space. I think the volume is so the first question is, if I'm using a rod mill or a ball mill or an HPGR or an autogenous grinding mill, AG mill, or a SAG mill, which of those affect the shape of particles? So the relationship between the milling device that you use for plant and the shape of the particles, do they come out looking like this, or do they come out looking like golf balls? That's a very important parameter, which we still don't know. We don't know which milling devices produce predominantly a particular shape. And also the mineralogy, or in English we talk about the competency of the ore, which means how hard is the ore. So if you're milling, sometimes some ores are very soft, some ores are very hard, and depending on whether they're soft or hard, they're going to break in different ways. So that will depend on the competency of the ore. But in terms of measuring, determining the shape, we say there's no standard methodology for particle shape analysis. So I said yesterday, you can buy an instrument from a company called Sympatec. What's the other one that we got? Camsizer. The Camsizer, Sympatec, there are different manufacturers. I'm sure China's got them also. But you can buy instruments using laser diffraction technology to determine shape. You can also use viscosity to determine shape. You can use an electron microscope to take the particles that you feed into the flotation, take them to electron microscope and look at the shape of the particles in the electron microscope. You can use an optical microscope. So there are many ways to look at the shape of the particles.
这里就是讲这个颗粒的这种形状，其实还是由上游的这种磨机或者是磨矿决定的，使用不同类型的这种磨机得到的这种颗粒的形状也是不一样的。另外就是这个颗粒的情况到底是怎么样的？你现在有比较多的这种检测方式，第一种就是比如说用扫描面去看它到底是什么样的形状，另外就是光学显微镜，还有是比如说你也可以用膜电影去检测这个颗粒的形状。
Right, now there are different ways in which to define the shape of a particle. The first is aspect ratio, and this little thing we've got in my hand is a good opportunity to show that. The aspect ratio, as you can see, is the ratio of the length to the width. So the length to the width is called aspect ratio. So that's the one definition of shape. The other one is called the circularity. That's 4 pi times the area divided by the perimeter squared. And that's got to do with formulas for surface area of the sphere and the volume of the sphere. So that comes out of the definition of volume, 4 pi r cubed and pi r squared. SEM micrographs, I mentioned that. You can go and look at a scanning electron microscope. Look at the volume keep on going. That can give you shape. You can use Quem scan. And in fact, I'll show some slides here where one of our former students, Lucy Little, used Quem scan to determine the shape. It's more time consuming, but it's very good. And then the apparent viscosity. This is a very good reference. Barnes, it's a book written by Barnes called Introduction to Rheology. It's a very good book. It's in the public domain. You can't Google it. Maybe you can Baidu it. and it's a very good book on rheology. And in that book by Barnes, he explains exactly how you can use viscosity to determine the shape, rods and plates and cubes and spheres. It's a very good book on viscosity, and the section on shape is what I'm going to be referring to. Thank you, Dr. Ray.
这里就是讲跟这种情况表面情况有关的几个参数，有几种表示方式，一种就是长宽比来算，另外一种就是它的比表面积比上它的周长，然后看出来它的这个不规则度。另外是这个扫描电镜，通过扫描电镜来看它这个表面形状。另外一个是就是用这种扫描电镜监测仪，就是地质常常用的这种 film scan， 然后来看它的这个表面情况。还有一种大家非常熟悉的就是油电仪，油电仪是一个非常有用的检测这个表面情况的一个仪器，就是通常在颗粒粒径大小相同的或者刚好分布相同的情况下，使这种棒状的这种粘度要大于这种片状的粘度，然后又大于这种不规则体积状的粘度，然后最后是这种球形的这种粘度是最小。
Right, so now we're going to talk a little bit about the measurement of shape. I already mentioned we can use instruments which use dynamic image analysis, which is laser diffraction technology. We spoke about the cam sizer, that's one type of instrument you can buy in the shops. Sympatech, I mentioned yesterday, Sympatech are actually using, they've got a lot of their instruments on concentrators in Chile, and some of the copper concentrators, where they online are monitoring the shape of particles, and these are very big concentrators. Escondida is just on the verge of opening, will be the biggest underground mine in the world. 140,000 tons an hour. So they're monitoring shape on such big concentrators. So these instruments are normally used primarily for size analysis, like the Malvern. You know the Malvern in China? It's a very well-known instrument for measuring particle size distribution. But now you can use shape, and you can see that here is an example of an image that you will get where you can start making predictions of shape. Obviously, this is heavily statistical based, because how many particles, you can see that particle there is clearly a high aspect ratio. That particle there is clearly spherical. How many particles you monitoring will also have an effect on your shape analysis. Then you can use scanning electron microscopy. EDS as a potential for characterizing finer particles. Here you can see an electron microscope scan, and you can see there's an example of a particle which is a high aspect ratio. That's more spherical. There are two particles, high aspect ratio. Now, I'm not sure what I'm talking about. Our colleague here from Kunming, you're a crane scan expert. I don't know how I think there must be some software to take those micrographs and do an analysis of shape. Is that how Megan does it? I'm not sure. I think there's software that they use. Because now we can see round, that's irregular shape. That's probably more high aspect ratio. That's very high aspect ratio. And so you can scan all the particles, take the images, and then you get a distribution of shapes. So all I'm saying now is that for many years we just looked at size, but now we're starting to understand we need to look at shape.
这里就是讲这个颗粒这种形状的启动检测方式。一种是这种 M size， 相当于是显微镜，但是它是两个显微镜对着一个样子，就是你的形状看得更全一点，或者说横向、纵向都可以看得见。另外一种是 sympathetic 这种的，就类似于一种在线可视的这种聚焦高速反射测量，它可以在你浮选的过程中，就实际况的浮选过程中，直接把它放到这个浮选槽里面，就可以看到在线看出来的这种颗粒的这种情况，然后对这种情况做一个检测和分布区域的分布，就可以看出你大概你这个浮选过程中有多少颗粒是这种不规则形状的，有多少颗粒是规则的，对他们做一个这种整体的分析。另外一种就是这种 相当于是扫描 DNA EDS 的这样的一个检测方式，它也是就是可以看出这个几种不规则形状的这个，就是多种不规则形状的这种颗粒，然后对它们进行一个分布，就是一个分布和相当于是一个半定量的计算，就是说大概有多少是不规则的，有多少是规则的，
So what is a very interesting research to do in your laboratory research is to take your concentrate and your tailings and take a sample of those to the electron microscope. Because I know the electron microscope has software to do image analysis to give you a distribution of shapes. And it would be very interesting, and we don't do that very much in our group, but maybe we should be doing more of it to see whether the shape of the particles coming out in the concentrate are more this shape, and the shape of the particles going in the tailings are more like golf balls. And it would be interesting to do that, to see whether shape is playing a role in your results.
这里就是讲，大家如果有兴趣的话，可以把这个你们浮选过程中这个金矿里面的这种矿，就是这个有机矿物，还有这个伪矿里面的这种矿物做个对比，就是形状上的对比，放到显微镜来对比。Dr. O'Connor 这个科技做了非常多的这样的研究和测试。如果你去做的话，也有可能会也会有一个这样的发现，就是说你的金矿里面的这个选上的金矿里面的这种矿物颗粒呢，多数是不规则形状，而伪矿里面多数是规则的或者是球形状。
Right. So this is the famous photograph. I showed it yesterday. For those of you who weren't here yesterday, these are gold particles which started out their life in the Alps. They went down the Rhine River into Germany, and my good friend Hermann Gotruba in Aachen, they did research. This was actually a project funded by the German government, where they did flotation on material in the Rhine River that they recovered. And these are gold flotation, and you're using diesel oil to float it, so it's true flotation. This is true flotation, where you make the particles hydrophobic. That's the concentrate, and that's the tails. And I don't need to tell you that you can see that the particles shaped like coins, they recover well, and the particles shaped like golf balls, they don't recover. And of course you can see here are some particles of stone, which obviously don't get recovered because they don't become hydrophobic through the diesel oil. But these are the gold particles, and you can see for true flotation, shape is very important.
这里就是讲一个在真浮选过程中，这个颗粒的形状到底是有多重要。就是说，他们是对金矿的这个浮选，做了一个调研，就发现这个浮选，如果浮选是金的话，发现金矿里面多数是这种像硬币一样这种片状形状的这种矿物，而在伪矿里面多数像高尔夫球这样就是球形的矿物。当然，大家看到伪矿里面还有一些不规则形状的这种石头，但是它这种石头是因为是清水，所以它还是在伪矿里面。这里讲的是真浮选，就是说全部是这种通过这个表面认识性上来的，不是说通过夹带上来的。
So here's a challenge to CSU Research Group. Can somebody get me another photograph one day of another sample where you show them that the particles that are in the concentrate are like that shape and the tailings like that shape? This is my only sample I've got. I want another example.
这里就是说，大家能不能如果有工作的话，能不能提供一份这样的图片给 O'Connor 教授？就是他现在有一份，如果大家有的话，可以再提供一份给 O'Connor 教授。
And now that you've got the best cell phone in the world called Huawei, which takes the best photographs in the world, you can take photographs of your concentrate of froth, and maybe you can see them the particle shape.
教授就是说，我们现在这个大家都有华为手机，可以分辨率可以非常高，可能你在浮选过程中多拍几个精细的照片，就可以把这个泡沫里面的这种金矿，还有伪矿里面的金矿给拍出来，然后可以发过去。
Right. So We spoke about this yesterday, but because this is all about shape, I want to repeat it again. The shape of the particles we get is often affected by the way in which the particles are comminuted or broken. So we spoke about abrasion. So abrasion is where slowly you wear away the particle. It gets smaller and smaller and smaller, and these particles will tend to be more circular. Okay, then the other type is compression. This happens in the HPGR. In the HPGR, the particles come through the rollers, and the rollers compress the particles. And when they compress the particles, you're going to get this like, so these are cleavage planes in the particle, and of course it's going to break like that. HPGR is widely used in the diamond industry. Because in the diamond industry, if there's a diamond there, you don't want to break the diamond, because the bigger the diamond, the more valuable. So HPGRs are widely used but they've used all over. The cement industry in Turkey, the biggest use of HPGRs in the world is in Turkey, in the cement industry. And then we've got impact. This is where you take a hammer and you hit the particle. We spoke about it just now. And then it's going to break into smaller particles. All of those mechanisms will affect the shape of the daughter particles. These are the particles resulting from the gradient.
这里就是讲这种不同的这种模矿或者破碎的方式对这种矿物形状的影响。第一个就是说，你如果是用摩擦或者是这种磨损的方式来进行的话，它通常得到的这种形状相对规则的这种矿物。如果是用这种，比如说是挤压的方式，比如说我们破碎的时候用这种 HPGR 这种，就是两个这种柱子然后挤压的矿压碎的这种。它得到的是相对不规则的这种矿，而且这种方式呢，多数在这种钻石的这种破碎的时候用的比较多，因为钻石它比较贵，然后你假如说就想破碎其中的人生其中的一块的话，就把边上的挤掉或者怎么样。第三种就是说你用这个锤子打击或者撞击这种的话，它会得到的形状也不规则，然后颗粒的大小。
So, as I said yesterday, even though we are doing flotation research, it's important for us to understand comminution, because the particles that we are putting into our flotation cell came from somewhere, and how they were prepared is going to make a big effect on our flotation. So, if you're doing flotation research, you must know about comminution, otherwise you're going to miss something.
教授这里强调就是说，如果大家做浮选，一定要对上游你这个破碎的方式和磨矿的方式一定要非常非常重视，非常非常注意，因为你的这种磨矿的方式不同，或者是你破碎的方式不同，会直接影响到你浮选的结果。
Right, and this is more of the same. And can we see an example of stirred mills, which we spoke about yesterday? And so you can see the way in which these particles break, abrasion or accretion. The previous slide showed that. Impact happens in ball and rod mills. So if you're using ball mills or rod mills in your laboratory, you will have mainly impact mechanism, and that's the sort of that we showed that these. You can see these particles are all irregular. So you may start with two spherical particles. You're going to finish up with particles with a wide distribution of shape. And then I spoke about the HPGR compression. And compressing is going to break the particle up. So this is really more of the same. So it's a repeat of the previous slide.
这里就是针对前面三种不同的方式对应的逻辑就是不同的。比如说这个摩擦方式对应的逻辑就是这种搅拌膜，它就多数是这种圆形的这种颗粒。然后通过这种撞击或者敲打方式用的多数就是这种球磨机和棒磨机。另外是通过挤压的这种对应的这种破碎或者磨击的方式，就是这种HPGR 或者说这种旋转磨击这样。
So the comminution people, and I'm not a comminution person at all, I'm a flotation person, but also you must remember each of these mechanisms will depend on the hardness of the ore. So if the ore type, the competency, let's call it hardness, if the ore is very hard, it's going to break a different way to the ore that's very soft. So you get hard ores and soft ores. You get a thing called Mohs index, M-O-H, and that gives you an indication of the hardness of the ore. And so there are different ways in which the ores can be characterized, and our colleagues in our research center do a lot of comminution research. They do a lot of modeling to model the hardness of the ores, because that will affect how the ores are broken in the mill.
这里还有一个因素，就是说这个矿，矿是这种软质的矿，还是质地较软的矿，还是质地较硬的矿？它们这种质地不一样，就是软的和硬的矿，它们对应，就假如说你用同一种这个磨机或者说破碎的话，它得到的形状可能也是不一样的。然后教授在这方面已经做了很多年的模拟和实验。
Right, and this, I'm going to move on to this slide. So, we've spoken now about how milling affects shape, and we've spoken about abrasion, and we've spoken about impact. I'm not going to spend more time on the slide. So, the point here is that often at comparable energy consumption, autogenous grinding results in better mineral liberation than grinding with steel media. And many times the particles also become rounder. So if you're using autogenous grinding, you get better mineral liberation, which is why we grind. We grind to get mineral liberation, but you also get particles which are rounder. This work comes from work of my good friend Eric Forsberg. So here you've got a problem, because we want to have better liberation, but we don't want to have rounder particles, because we've seen rounder particles don't float very well. So the question here is, you've got it's optimization between the type of grinding you use to get better liberation, but what happens to the shape of the particles. And so here we see ores suitable for autogenous grinding usually break along the grain boundaries to give you complete liberation. And this was a paper written in 1988, where Eric said, in future, studies of shape and liberation will be of ever increasing importance. That was 30 years ago, that Eric Forsberg, a very famous mineral processing person, said, ever more important. But since then, there hasn't been a lot of work on shape, and that's why I'm emphasizing it in this presentation.
这里就是讲的这种磨矿过程中这种解离度和这种形貌之间的一个关系，就是说，比如说用这种自动的这种磨机，你想要达到一个同样的这种用同样的能量去磨的话，发现就是说你达到一个你的磨矿的解离度达到了，但是你可能得到的这个颗粒呢是这种我们前面说的那种不想要的球形的表面光滑的这种颗粒，就是说这个解离和这个矿的这种形貌之间是一对矛盾。你想要的可能是解离，但是解离之后这种矿物的形状呢就是你不想要的。所以就是说我们以前只强调说这个解离度很重要，但是现在要强调的就是解离度和形状是同样重要的。
Right, so here we see some examples we're starting to look at of a hammer mill and a piston die, and you can see how we're looking at the distributed normalized frequency and angularity. Now the higher the angularity, the more the shape is like this. Okay, and when angularity is very low, then in fact the shape is more round. So you can see these are round particles. These are highly angular particles, and what's happening now is we're getting quite a wide distribution of these particles. So this is typical of the sort of results you're going to get in terms of the breakage mechanism. Here we're using a piston and die, and a piston and die is where you just literally smash the particles with a piston coming down on top of the particles, and here we see that in fact we're getting particles of many more particles of higher angularity. So that you can see now the difference. It's a small difference, but it may be very important. Here's the reference. And so these particles, a hammer mill and a piston are simply showing you the proof illustrate that the type of breakage mechanism will change the distribution of particles of different sizes. And now we've seen that these particles, which are more spherical, they won't be so good for true flotation. These particles will be very good for true flotation. But as I will show just now, these particles also entrain more rapidly.
这里就是讲了两种不同的这种破碎方式对这种矿物形状的影响。前面是一种采用这种磨的方式然后进行的，然后它的这个颗粒的这种不规则度或者角度相对窄，就是说明它就是说相对这个不规则度相对小一点。而后面用这种挤压或者是压榨的方式，然后进行这种破碎或者是磨的话，它的这个风就会向右移，或者说它的不规则度会增加。
By the way, you can see that if you look at this picture, these are the particles, and so you can see those angular particles, that's angular particles, spherical particles. So what you would have to do is look at every particle, and I think this is what sometimes people are doing. You sit with a pen and paper, and every particle you describe it, angular, not so angular, but now the computer can do that for you. So you can download from the computer free software which does image analysis, and that's the way you do that these days. Now you can see there are more particles that are highly angular. You can see them here. There's one there, and so these particles will result in more angularity. So the computer does it for you.
这里就是讲大家在浮选的过程中得到这个矿物呢，你可以用这个，你可以一个一个的计算这种你这个颗粒到底的不规则度有多少，是圆形的还是不规则的，不规则的边有多少。当然大家可以用计算机，然后就把这个照片拍下来以后，让计算机计算到底有多大的不规则度。
Right, and so here we see again the effect of the grinding device on particle shape. This is more of the same, this is frequency. This is now roundness. So we're looking at a distribution of roundness. So you can see that these are different feeds, ball mill feed, isomill feed, isomill discharge. So these are different types of ores. Now, the interesting thing about this, we've got different types of ball mill feed. So this is the feed to the ball mill, feed to the isomill, the isomill discharge. And just let's look at this for a moment. The little red triangles, that's the discharge. There. Okay, those red triangles. The feed is the blue circles. And now what happens? The feed and the discharge have got the same distribution of particles in terms of roundness. So the roundness frequency these are in the 53 to 75 fraction. No difference in shape characteristics for plant samples. This was Lucy Little, one of our PhD students. And so this means to say that actually it makes no difference. The feed and the product have got the same size distribution.
这里就是讲他们这种进料的时候，这种就是你在不同的这种你用不同的这个磨机得到的这个物料，你进料的时候对这种你的这个物料里面的颗粒型号进行一个分析，然后选矿完了之后，你再对这个颗粒的这种形状进行一个分析，发现这个不同的，比如说你用不同的磨机，我们得到的这种在实际矿上，这是矿上的一个数据，就是在实际矿上你发现是一样的，就是这个它用棒磨机得到的这种物料，还有用这种ISA 磨机得到的物料，然后在选矿完了之后再对这个物料分析，发现这个曲线几乎是一致的。
Now before I move away from the slide, this slide says I should finish my talk now because it makes no difference. But this is ore dependent. Another ore going through the isomill may look like this. So it will depend on the ore type. If I had an ore like that, it would be quite different. So different ores will behave differently depending on their characteristics that I mentioned earlier.
这里就是讲
你看上去是一致的，但是你如果换一个矿的话，它可能就完全不一致，又跑了。就是说，你可能说有的时候啊，你这个矿是一致的，觉得这个形貌或者说你这个形状的分布可能对它影响不大，但是有的时候影响是非常非常大。
Right, and so this is more of the same, and now you can see we are now looking at again. Here we've got different sorts of ores. Ball mill ultrafine grind gives you most angular particles, followed by ball mill fine grind. So the SMD, which is the triter ultrafine. So depending on different types of milling, you will get different distributions. And so here I'm not going to go into detail about it, but here you can see an example. That's one particular type of mill. That's another type of mill. So these particles have got a different distribution. So in terms of frequency, these particles have got a roundness average value of about 0.3, and these have got about 0.5. So there's a different distribution depending on the types of mill we're using.
这里说了另外一种矿，但是另外一种矿它用了不同的这个磨矿方式进行之后呢，它这两个的这个矿的这种矿样的这种力度分布，就是形状分布是完全不一样的。比如说这个蓝色的这根线，它的这个圆形的这个大概这个圆形度吧，叫 roundness， 大概在 0.3 左右，而红色的这根线呢，大概在 0.5 左右，这个差别还是比较大的。
Right, now I mentioned this yesterday. Here we are looking at, all I'm going to talk about here we're looking at relative viscosity in solids volume. This comes from the book by Barnes. So now we are using viscosity as an indication of the particle shape. Now these particles are more needle shaped and these particles are more round. So we can see that this is a base metal sulfide, copper, lead, zinc. In fact, it's mainly copper, nickel. And so here you can see that in fact these shapes, the shape of these particles, I get myself a bit confused. Let me just remember. But the rheological measurements did. So these particles are more needle shaped, and these particles are rounder. So these are round particles, and those are needle shaped. Now the difference is that these particles have gone through the mill for different times. The point here is that if you compare that value, 2.5, the viscosity at 2.5 at that 40% volume, and now we look at this ore here, that's about 0.7. So you can see the platinum, these are platinum group minerals. The platinum group minerals behave quite differently to the base metal sulfide. So this emphasizes again that the shape of the particles will be strongly dependent on the ore type. This is a base metal sulfide. This is a platinum group mineral.
这里就是用流变仪，然后同样进行这个测量流变性的时候，同样发现就是说不同的这种颗粒的形状对这个不同颗粒的形状对应的流变性也是不一样的，而且是对不同的矿物它的这个形状是不一样的。比如说对这种金属硫化矿，第一个图是金属硫化矿，它的这个紫色的这个就表示它这个粘度特别高，而且它这个不规则形状特别多，就是比如说像针状的或者棒状的。而底下的铂金族的矿呢，它的这个不规则形状相对少一些，然后它的相对粘度也就小一些。
One final point. This is a discussion that we have in our own center. Some of these results, the SEM imaging didn't show any difference, but the viscosity measurements did. So the question is, which is right? Is it the QEM scan or is it the rheology? I personally believe the rheology gives you a better indication. The QEM scan is too dependent on the image analysis of those many particles. But my colleagues in the mineralogy group, they think the QEM scan. I think the rheology, because you've got a bulk sample, many thousands of particles. But that's a discussion point.
这里就是他们课题组内部的一个讨论，就是说 你用这个 SEM 这种图像分析呢，发现这个图像上面两种矿的是没有区别的，或者区别不大，几乎没有区别。但是你用流变仪呢，发现这个一下就做出这个区别还是很明显的，大家看到。就是教授呢认为是流变仪更可靠，然后课题组关于做这个形貌方面的人，当然认为自己的这个形貌分析也是非常准确的。然后大家不知道有什么看法，反正教授认为是因为你这个流变是测的是一个整体的，就是整个这个矿浆的这个它是一个，而你的这个图像分析你可能是一个二维的，或者说是部分的，不可能是就是这种完全的一粒都不放过的这样的。
So again, just to why am I spending so much time on this? Because we're talking about flotation. I'm spending time on this because if that's going to be your product from your milling, those particles are going to behave differently in the flotation cell compared to those, just because of their shape, not because of the reagents you're using, or the type of flotation cell you're using, or the type of depressant you're using, or whatever. The shape will actually have a major impact. So unless we understand that we, from different mills, you see, we're looking here at an isomill versus a ball mill. So the isomill, that's 4 passes through an isomill, and that's a ball mill. So the ball mill and isomill are going to give you different predominant shapes, and that will affect the flotation behavior of the ore.
这里就是还是讲这种不同的这种磨矿方式，他们用了棒磨，也用了埃塞磨机，他们2个不同的磨机，然后得到了这种颗粒的形状是不一样的，然后后面他们这种浮选的结果也是完全不一样
的。Okay, let me move on from this. And here we have more, and I'm not going to take too much time on this now. Here we have a simple example of using an electron microscopy photograph. So here we have particles coming out of a rod mill, coming out of a ball mill, coming out of a stirred mill. And again, we're just plotting here the different distributions. So again, it just emphasizes that the type of mill you're using, the comminution device you're using, will affect the shape of the particles.
这里就是用不同的磨机得到这个矿物表面的这个形貌的图片。底下这个就是一个这个图片的一个量值的一个分析，就发现这个用不同的磨机，比如说这个搅拌磨，还有这个球磨跟棒磨得到的这个曲线是不一样的，图片也是，就是形状也是不一样。
Now the second important message from this, these particles started out as spheres. They were spheres and they were ground in 3 different mills, a rod mill, a ball mill, and a stirred mill. And then what happened was there was tests done in a batch flotation cell using only frother, not collector, to look at entrainment. And what we are showing here is that the highest degree of entrainment was the rod mill and the lowest was the stirred mill. So these particles entrain, not float, entrain. That means they get into the concentrate without any reagent present. These particles entrained much more than those particles. Now I think if you look at the pictures, you have many more rounder particles in this sample here compared to here where you've got many more irregular shaped particles. That's just a superficial impression. So the particles that are more irregular, particles that are shaped like this, they entrain much more rapidly than particles shaped like golf balls. We showed earlier the gold picture was flotate, true flotation. Now I'm talking about entrainment. That means the particles simply report to the concentrate as a result of their momentum moving through the pulp. So particles shaped like this will entrain much more than particles shaped like golf balls.
这里就是讲用这个3种不同磨机，然后对它进行一个夹带的测试，就是说在浮选在就是做夹带的浮选的时候，就是说不加捕收器，只加起泡器，看它弗兰的我们假设就是弗兰的全部是由夹带产生的。那它这个上层这个基框里面呢，发现这个用
棒膜基产生的这种夹带的是最多的，而用搅拌膜产生的夹带是最小的。我们也看到这个棒膜基产生这种矿物的颗粒的形状是不规则的，更像一根笔或者是棒状或者是针状，而用这个搅拌膜基产生这种矿物的颗粒的形状多数是相对规则一点的，类似于球形的。
In the laboratories here at CSU, do you use rod mills or ball mills? Ball mills. Both.
Yeah.
Which do you think you should be using? Well, you probably, I mean, a ball mill looks like you have less entrainment. Also for true flotation. So, open question. Okay, this is more of the same, and this simply, I showed this picture yesterday. These are samples of wollastonite. Wollastonite is very well known to have a needle-shaped particle like this. And these are ballatini. Ballatini are perfectly round. They're all like golf balls. And so here we're looking at viscosity. This is again from Barnes. There's the book I spoke about. The Handbook of Elementary Geology, I thought it was introduction, it's called Handbook. So you can see the ballatini have virtually zero viscosity, and the wollastonite very high. This is simply to show you that using viscosity is a very good way to estimate the shape of particles. The highly irregular particles have a very high viscosity, the round particles very low viscosity. Simply to illustrate, it's a good way to measure, to get an indication of the shape of the particle.
这里还是强调这个游裂仪是对矿物表面形状的一个非常有效的检测方式。左上角这个图就是 wollastonite， 然后它这个形貌是多数是针状的或者棒状的，它的粘度就非常非常高。而右下角这个 ballatini 呢，它是多数是球形的，所以它这个粘度就几乎是零，非常非常低。
By the way, we buy our ballatini from Japan. I'm sure in China you can buy ballatini. It's very good to have it in the laboratory for tests, for doing tests on round particles. I'm not going to look at that slide again, and I'm not going to look at that slide. This is the slide which I've been talking about. This is from Barnes, viscosity against phase volume. You can see if I take a constant phase volume, the round particles will have very low viscosity, the needle-shaped particles much higher. The picture's gone off a bit in terms of scale. This simply illustrates what I was showing in the last slide. I'm not going to talk more about it. Okay, I've shown that picture already. Influence on true flotation. I showed this picture yesterday. This is using ballatini, and you grind the ballatini to different shapes. And so what we see here, these are ballatini of different sizes, and now they've been crushed in a mortar and pestle. And you can see this is true flotation. That's the spherical particles, and those are the ground particles. So this picture again shows you that the more irregular shaped particles float better.
这里还是讲这个矿物的形状对浮选速率的影响，就是这个粉色这根线呢，它是圆形的这种 ballatini 的这个线，然后上面是不规则的这个形状的，发现不规则形状的它的浮选速率就比这个规则形状这种球形的要远远的要高。
This is the work of Peter Coe from Cyril, Australia. They did a lot of work about 10 years ago on this sort of work. So that's a good reference, Peter Coe from Cyril in Australia. Right, I'm not going to look at that any further. Here we are looking at, now what we're plotting at here is flotation recovery against fractal dimensions. Let me just say, that means particles, there's a spherical particle, there's an irregular shaped particle. The message of this slide is that the red lines show the contact angle of the particles. And that's these particles here. These round particles have a low contact angle, 61 degrees. These irregular shaped particles have a contact angle of 78 degrees. These are more hydrophobic than these particles. And so you can see that in terms of flotation recovery, this slide's a bit confusing, but the particles, the green particles, of higher contact angle. So the more irregular shaped particles have higher contact angle. That's the story of the slide.
这里就是其实这种矿物的形貌，它们对应的这种表面润湿性也是不一样的。比如说球形的，它这个规则的球形的这个矿物表面这个润湿性呢相对低一点，就是图里面这根红线最低的61，然后这种最不规则的这个呢，它的这个表面润湿性就是疏水性反而是更高一点，就是说78，就是图里面这根绿线，大家也可以看到，就是说这个表面形貌和这个疏水性是成正比的，越不规则，它这个疏水性越高，所以它这个回收率也是越高的。
Essentially, this slide is showing the natural floatability. And just to make the point, if you're doing studies of natural floatability, you must use a size range greater than 38 microns. Otherwise, you're going to be measuring entrainment, not natural floatability. So this is natural floatability of particles in the 38 to 75 micron fraction. So it's natural floatability. It means floatability in the absence of a collector. But what I'm saying is that when you use a microflotation cell, you must use particles bigger than 38 microns. Because those smaller ones will just entrain. Then you're confusing entrainment with natural floatability.
这里就是强调，就是我们浮选过程中，通常就是大家选这个颗粒粒径的时候，通常是用大于38微米的。原因就是说，小于38微米的这种颗粒，它通常是通过夹带上去的，会影响到你这个浮选的计算结果。
Right, now this is the end of the talk. It's talking about the effect of particle shape on entrainment. Now, why we were interested in this is that I mentioned in my talk the other day, in platinum group minerals, you don't want to recover chromite. And chromite seems to be recovered by entrainment. And this research was to look at the effect of shape on entrainment. So what we did was, we took ballotini, we took wollastonite, you could see again the wollastonite, needle shape, these are like golf balls, and then we took mica, talc, and vermiculite as other minerals. And let me just move on. So here we are looking again at viscosity against the solids percentage, and you can see there's the wollastonite, and there's the ballotini. Let me just focus on those. We've seen the wollastonite has an aspect ratio greater than 1. Ballotini is an aspect ratio of 1. That's a sphere. And so you can see that the wollastonite entrains much more readily than, has a higher viscosity than the ballotini. Let me leave the others for the moment. So to start with, we're looking at wollastonite, needle shape, ballotini round, and the apparent viscosity is a way to measure that. I think I've covered that already, so let me not stay with, let's move on. And then this is using QuemScan for the same purpose. Now what we're looking at is again different particles of ores, and again we're using viscosity, and I'm going to go a bit quicker here. So now we have entrainment. How do we measure entrainment? We measure entrainment by looking at the solids against water. And from the famous work by Treha, entrainment is indicated when the plot of solids versus water is a straight line through the origin. Through the origin. By the way, it's got to go through north, because you can't have 5% solids or 5 grams of solids if you've got no water. Life doesn't work like that. So if you plot the data, it's got to go through the origin. All of these are straight lines. All of them are straight lines. That means we're getting entrainment, and the experiment was done that way. We did the experiment in a batch flotation cell, no reagents, just turn on the air and check to see whether or not we're getting recovery. And the point of this graph is that the ballotini entrain much less than the wollastonite. So the story of this graph is when the particles are more needle shaped, they entrain more readily than when the particles are like golf balls. So the round particles do not entrain very much. The needle shaped particles, they entrain.
这里是讲这个浮选过程中夹带的一个计算。大家知道浮选过程中，你把这个矿物这个总的这种质量称出来，然后横坐标是它总的这个水的量，然后它比下来，如果是一条直线的话，就表示它夹带的程度。然后上面这个就是不规则形貌的这个volatility 呢，然后volatility 呢，它是这种针状的，然后它是夹带程度非常高的，而且这种球状的 volatility 呢，它这个夹带相对要小很多。
And the other day, Belinda spoke about entrainment factors, just to show you that here we've got elastinite, entrainment factor 0.0146, that's Ballatini, you can see it's smaller, and here's chromite. So there's Ballatini. The Ballatini, very low entrainment factor, elastinite high, and there's chromite. So you can see chromite is recovered through entrainment. That was the purpose of this research, to check how is chromite recovered, and it's recovered through entrainment. Large particles. Now, before I finish this slide, chromite's very heavy particle, high density, and yet you can see it entrains very rapidly. So how come a very heavy particle in a flotation cell should go down to the tailings, but the chromite entrains to the concentrate? How come? Because of its shape. I spoke about hydrocyclones earlier. In hydrocyclones, the group in Japan has shown very nice research, heavy particles reporting to the overflow because of their shape, and that's because of drag forces. But so the shape of the particle is more important than its density.
这里就是讲这个对 Ballatini 这个球形的来说，不管是它小于25微米的，还是大于75微米的，它的这个夹带因子呢都非常非常小。而对于这种铬铁矿来说，它不管是小于25微米的，还是大于75微米的，它这个夹带的因子都相对大，说明这个铬铁矿它主要还是通过夹带上去的。而且因为这个铬铁矿它的这个形貌是跟这种 Ballatini 是不一样的，它是不规则的，所以它更容易通过夹带上去。
I'm not going to spend time on the slide. This slide is simply the story of using how drag forces explain why needle-shaped particles entrain. It's all to do with that famous equation. These are the drag forces, and you could show very clearly that the drag forces are much higher for particles like that and for particles like that because of the drag coefficient. But I'm not going to spend time on this now. So, the conclusion. Particles in the same size class, but with different shapes, have different entrainment properties. So it's not just about size, it's also shape. And then secondly, the classical linear relationship between solids and water confirms entrainment as the mechanism of recovery. Shape effects are dominant even when surface charges are different. What we did here was we looked at the zeta potential of these particles to see whether the surface charge may have an effect. It doesn't have an effect. And finally, interestingly, coarser particles normally would give you lower recovery, but the particle shape effects are sustained. Even when you've got coarse particles, the shape is the dominant effect.
这里就是对这节课的一个小结。首先说就是说我们通常会比较重视这种粒径，但是如果相同粒径的情况下，不同的形状，它的这个夹带也是不一样的。另外就是说我们这种传统的做的这种夹带的这种曲线图，也进一步就是证明这种夹带对这种浮选的影响，就是说不同形状的这个矿物呢，它的夹带是明显不一样的。另外就是说大家经常做的这种动电位、表面电位到底对它影响多大呢？教授认为表面这种形状比动电位影响更大。另外是这种大颗粒的我们通常认为这种大颗粒的呢是这个回收率是相对低一点的，因为它太重了这种的。但是如果它的形状是不一样的或者改变了，它可能这个回收率也会上去，也会影响这个浮选的结果。
So just to wrap up,
there's what else does shape effect. Shape can also affect induction time. Belinda spoke the other day about the work that she and her colleagues are doing on induction time. And here we have some examples where shape can affect induction time, and I'm not going to go into detail of it, but that is the time for the particle to attach to the bubble.
这里就是讲的夹带里面这种矿物的形状对这种 induction time， 就是说这种矿物在这种气泡上面这种就是跟气泡碰撞，然后粘到气泡上面的一个时间过程。
And now I've spoken about this before, the effect of particle shape on classification. And so in a hydrocyclone, we have found that with coarse particles and gas flake to the underflow decrease. So what we have found again in a hydrocyclone, the shape of the particles makes a big difference. I spoke about that right at the beginning.
就是还是前面教授讲到这个旋分分流的时候，大家通常认为是重的在下面，然后轻的在上面。但是如果这个重的这个颗粒它是有不规则形状的，它也会上去，然后影响到就是底下这部分 underflow 底下这部分反而会减少，因为它是很容易夹带上去或者是浮上去的。
That's the work I'll be talking about by the group in Japan, where they did some very nice work on this. And so the final slide, the overall conclusion, the take-home message of this talk is that different grinding procedures produce particles of different shapes. Irregular shaped particles are more easily recovered by true flotation due to contact angle or hydrophobicity differences compared to spherical particles. True flotation, that's the picture of the gold particle. Needle-shaped particles entrain more readily due to the effect of drag forces. So that's the take-home message of my talk.
这个是整体的这节课的一个总结。首先说我们这种不规则形状的这种矿物呢，是由上游的这种模矿或者破碎决定的。另外这种不规则的在真浮选中，这个不规则的形状的这种矿物是更容易被回收的，因为它的疏水性是更高，就是说疏水性是更高的，相对于这种球形的来说。另外就是这种针状的这种矿物呢，它的夹带也是更高的，由于它这个叫牵引力因为相对高一些。
Thank you. So Belinda, a little break.
We do a 5-minute break.
5-minute break, and then Belinda's going to talk about her favorite topic, frost. What is entropy? What is entropy? Shock. And entropy?
Entropy shock.
Shock.
It's on the speaker. Anyway, doesn't matter. I have a problem. It's not because sort of that I'm not
the separation point absorption of
40 kilojoules per mole.
calories.
Kilojoules, not calories.
Kilojoule.
Kilojoule, yes. And in it should the they use
chemical bond between organic compounds.
Which will get it? So I don't think we're talking about the same thing. Because what I'm talking about is a chemical reaction on the mineral surface needs to be about 40 kilojoules. Well, not more negative than 40 kilojoules per mole. There's a textbook by on physical chemistry by Atkins. ATKINS. Okay, it's a big
It's a very good friend of mine.
I think we should carry on. Right, good morning everyone. And so as Prof O'Connor says, I'm going to be talking to you about froths this morning. And you can separate a flotation cell into a pulp zone and a froth zone, and you will often find that things that are good for the pulp zone are bad for the froth zone, and the other way around. So it's very important to think about them differently, a pulp zone and a froth zone in two separate components.
Dr. Belinda 这节课主要讲的就是这个泡沫层的浮选过程中泡沫层的一些问题。我们知道浮选呢主要分为两个，浮选里面实际上分为两个部分，一部分是泡沫层，一部分是矿浆层。因为这个泡沫层呢可能就是有用的矿物多一些，矿浆层可能就是没有用的这种矿物多一点。所以这个因为这两个性质不一样，然后这个区域也不一样，所以非常值得大家去思考和学习。
So let's start by taking a look at the froth and see how it actually looks. So this is a structure of a froth. We're going to be talking about things called plateau borders, and those are the channels through which, that's where most of the liquid lives in the froth, is in those plateau borders. The films around the bubbles are very, very thin. All of the water lives in these plateau borders here. And when your froth drains, the water drains through these channels of plateau borders.
这里讲的是一个泡沫的结构。大家知道这个泡沫表面这个水是非常非常薄的，但是在泡沫和泡沫之间呢，会存在这种 plateau borders， 就是这种边界，它的水是相对很多的。然后这些水呢也会在浮选过程中通过一定的力往向下走，然后那个有用的矿物被我们选上。
So how are froths stabilized? Well, they can be stabilized either by surfactants, or frothers, where you have a polar head group and a non-polar chain, and the non-polar chain goes into the bubble. The polar head group sits in the water and it forms the stabilizing ring around your bubble. Or it can be stabilized by particles. And you get particles, if this is a bubble, 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 you get particles that sit along the interfaces, and they provide a barrier to stop the particles from coalescing, from coming together.
这里就是讲这个泡沫层中这个药剂的分布，或者说是表面活性剂捕收剂的这种分布。我们知道这个它分为两个集团，一部分是清水的，一部分是疏水的。然后疏水的呢，一般会在这个气泡的里面这个集团，然后清水的就在气泡的表面，在这个水层，就是水的这一侧。 然后第二个图呢，就是说这个我们比如说三个不同的气泡啊，中间形成一个这个边界的这个周围呢，又是这些药剂的分布，然后这个药剂的分布呢，又会阻止这个气泡它会就是合在一起会破裂这样。
So, and in my experience with all the types of particles and surfactants that I've worked with, we've always found that the particle stabilized froths are always more stable than the surfactant stabilized ones. But Dr. Wang has had some experience of the other way around. So it can be that surfactants are very good stabilizers with froth as well.
Belinda 呢认为说是这个气泡表面这种矿物对这种气泡的稳定性要大于这种药剂对气泡的这种稳定作用，大家是不是这么认为？也可以考虑一下。
So if we look at a froth structure at increasing liquid fraction, so this is where you have no liquid, basically it's just air, and here you have 100% liquid, it's all water. And in between you can have a bubble sort of structure. In this region over here is where we usually find our flotation type froths. Flotation froths have very little water in them. This point here is called the jamming transition. It's where bubbles can move past each other. They start to act more like a liquid. In this region over here, a froth acts more like a solid. It's more like a solid structure. It can't move very easily past itself.
这里是讲了就是这个泡沫结构的这个随水的含量不同的结构。那没有就是说，首先是没有水的，最多就是完全是水的。紧接着没水的旁边这个就是说泡沫是形成了，但是它泡沫的边界里面的水是特别少的。这种泡沫通常是特别干的，不容易流动或者是移动的。然后旁边这个呢，就是说这个泡沫和泡沫之间的水相对要多一点，它可以在泡沫之间相对滑动或者走动，致使这个泡沫这个流动性也相对大一些。
So we must also remember that when you have a froth of this height in a full-scale flotation cell, that the bubble size changes from the froth interface all the way up to the top of the froth structure. So you have much smaller bubbles at the bottom. They are only at around 1 millimeter, the size that the bubble is made in the pulp zone. And when it crosses across the pulp froth interface, it's at about 1 millimeter. Whereas it can go up to many centimeters at the top of the froth itself. So during that change in size, there's a large change in the liquid content of the froth. So you go from very watery froth at the bottom to a froth that's very dry at the top of the froth, because the froth liquid content is approximately inversely related to the square of the bubble size. So this is the length of a plateau border, inversely related to the square of the bubble size. The length of a plateau border, remember the plateau border is where the water resides. So at the pulp froth interface, the liquid content can be tens of percents, 20%, 10, 15, 20%, whereas in the overflowing froth, your liquid content is usually less than about 1%. You're about more than 99% air and about 1% water.
这里是主要讲这个泡沫的结构，就是前面上一页那个图的一个横向，你把它倒过来转90度看的话，转90度看的话，就是说，这个首先说这个泡沫的这个大小，就是气泡的大小，它是接近矿浆相的时候，它的气泡是最小的，然后随着就是越往上越往顶部这个泡沫的顶部的时候，它这个气泡是最大的。 另外从含水量看的话，就是说越靠近底部，它这个气泡里面这个泡沫层这个水的含量是最高的，而靠近底部水的含量是特别少的。而这个水的含量是跟这个泡沫的这个跟这个边界的这个大小是有关的。你这个边界这个越大，刚才我们看那个三角形那个边界，它是越大的话，它这个水的含量就越少。就是这是一个呈反比的状态。另外是就是说我们在浮潜过程中靠近矿浆的那部分的泡沫里面，大概含水有10%左右或者更高，而靠近顶部的时候，那个水的含量就非常少，可能会少于1%或者更少。
So this is from a laboratory study in Graham Jamison's laboratory, just to show you how the bubble size can change as you move up the froth. So remember, this is only in a froth about so big. Well, how big? It's that is 40 millimeters. Okay, so it gets quite high. So that's at the pulp froth interface. That's at about 200 millimeters, and you can see how as the distance from the interface increases, so your bubble size increases. And you can actually measure the stability of the froth in that way. So if your bubbles are coalescing, then you are going to get bigger bubble sizes. The slope of this will be steeper. So that is a less stable froth, and that's a more stable froth.
这里就是一个这个泡沫这个大小跟这个泡沫距这个就是泡沫相和矿浆相这个界面的这个距离的一个关系，就是说越靠近这个矿浆相这个边界的，然后这个泡沫是越小的，越往上，它这个泡沫是越来越大的。而且根据这个呢，也可以算出泡沫的稳定性，就是说可能你这个泡越大，两个泡之间它会破裂，然后合成一个，越大是越不稳定的，而越靠近这个边界的这个临界的这个地方，然后它是越稳定。
So what affects the froth stability? What contributes to making a stable froth? Well, we have a few direct effects. So there are the effects of the particles and the effects of the surfactants. For the effects of the particles, it's mostly the hydrophobicity of the particle, the size of the particle, and the amount of them that you put into the froth. That's what affects the froth stability. And in terms of surfactants, it's the chemical structure of the surfactant and the concentration, the amount of it that you use.
这里是讲影响泡沫稳定性的几个因素，主要是这么两个因素，一个是这种矿物颗粒对它的影响，另外一种是药剂对它的影响。矿物颗粒的话，就包括矿物的这种表面润湿性，或者它的大小和形状，还有就是它的总共有多少，这个泡沫里总共有多少矿物。这个药剂的话，主要是包括药剂的分子结构，还有药剂的浓度。
Then you have many indirect effects that can affect the froth. But all of these indirect effects affect basically the particles, either the hydrophobicity of the particles or the amount of particles that are being put into the froth. So there's things like depressants and collectors. They both affect they make particles either more hydrophilic or more hydrophobic. You have things like air flow rate, froth height, froth residence time, energy input. They will all affect the amount of the particles that you put in the froth. So it comes down to quite simple. The direct effects are quite simple, are just particles and surfactants. But there are many different indirect effects that can affect how much of the particles or how hydrophobic those particles are.
这里还有一些间接的因素也会影响到这个泡沫的稳定性，比如说这个抑制剂、捕收剂，还有这个充气速率泡沫的高度、泡沫的这个保留时间，还有一个能量的输入。比如说你加入抑制剂和起泡剂，你就会影响这个 这个矿物的表面温湿性，然后进一步影响这个泡沫的稳定性。而这些呢又会这个不管是抑制剂起泡剂、抑制剂捕收剂，或者是充气量、泡沫高度，还有泡沫的保留时间，还有这个能量的输入呢，又会影响这个上层泡沫中这个矿物的整体总量，然后它又会接着影响泡沫的稳定性。
So we said that it's mostly the particle size and hydrophobicity, those two that affect your frost stability. So let's look at some examples of how size and hydrophobicity can affect your frost stability. If these are bubbles, the darker areas are the bubbles, and this area here is the plateau border, the film between your bubbles. The drainage of that film is affected by the pressure differences between those. So, in this example over here, it's this one, you have large, low hydrophobicity particles that bridge that film, and they form a boundary to the bubbles coming together. They stop the bubbles coming together. In this example here, you've got small, very small, moderately hydrophobic particles, and they can alter the radius of curvature, and so they change the pressure and therefore the drainage between these. In this example, you've got flocculation. So you've got networks of particles which actually stop drainage occurring. And in this case, you've just got hydrophilic particles. They're not even attached to the bubble surface, but they can alter the viscosity of those films between the bubbles, and they can hinder the drainage because of the increase in viscosity.
这里讲了影响泡沫稳定性的几个因素。我们知道这个颗粒的大小，还有颗粒的那种疏水性会影响到泡沫的稳定性。比如说这个泡沫里面，如果是没有这个颗粒，然后它是两个气泡之间是一个水膜，就是一个边界的水膜。但是如果有颗粒的话，它会就是把两个气泡然后桥连在一起，就是像图中的 B 和 C 一样。另外就是说，如果这个颗粒又非常小，然后它们自身有一定的这种去凝作用，会把两个气水性，它根本就不会粘附在这个气泡上的话，它会在两个气泡之间的这层这个水膜里面，但是它会阻止这个水膜的下滑，因为这部分东西呢，它这个粘度相对高一点，因为固体的含量相对高嘛，粘度相对高，所以它会有阻止水下去的这种倾向。
So this is just an image, a photograph that I took on site, 2 different photographs, just to show you how minerals can affect froth. So here you can see this, let's suppose there's a flotation cell underneath there somewhere. You've got this very stable froth. It won't break down, it's flowing over the edge of the cell. It's very difficult to manage. And I've seen this particular plant go from a very manageable froth to a very unmanageable froth very quickly when the ore type that's being fed to the plant changes.
这里就是讲，这是一个选矿现场的一个这个图，就是说这个泡沫呢，它是非常多，你看这个性状也相对来说是不可控的。它就是说，在选矿过程中，它这个如果你这个矿物的类型改变的话，它这个泡沫有可能一下子就变掉了，从非常好、非常理想的那种状态，变成一种非常不可控、非常难处理的一个状态。
So we said that it's mostly particle size and hydrophobicity that affect the froth stability. So let's look at some data that comes from a PhD student of mine. And what we're looking at here, this is the froth stability, and this is the contact angle. So how hydrophobic are these particles? And these are particles of different size. So this is an average size. These are small particles, and these are large particles here. So what you see when you look at the small particles, as the particle becomes more hydrophobic, the froth stability gets more and more and more until you get to a certain point that's just below a contact angle of about 70 degrees, and all of a sudden your froth stability decreases. And it's much more pronounced for the small particles than it is for the large particles.
这里就是讲的这个颗粒的这种表面润湿性对泡沫的稳定性的影响。我们看到这多数情况下是随着颗粒表面润湿性的增大的话，它的这个泡沫的稳定性也是增大的。但是对这种小颗粒的，就是大概28微米的这种小颗粒矿物来说呢，随着表面润湿性的增加，它一开始泡沫的稳定性就增加了。当它增加到70以后呢，随着它这个接触角进一步增大，表面润湿性进一步增大，但是它的稳定性会突然下降。
So this is looking at looking at a video that I took on site, and this one here, it's a cleaner cell, and that's sort of a normal, stable froth. It's what you'd expect. You have some bubbles bursting, but it's a normal looking froth. But if you take a look at what's going on in the first cleaner cell, what you can see here is the bubbles there's these valleys here, and as the bubbles start to burst, there's this chain reaction, and you just see these bubbles bursting all the way across the froth. And this is to do with, this is a first cleaner cell, very hydrophobic particles there, and you can actually see in those little valleys there very gold color particles. It's the chocolate pyrite, they're very hydrophobic, and they're causing this instability in the froth. And you can see the difference between those two cells in the froth and how they look.
这里是两个浮选的两个泡沫的图的实际浮选过程中泡沫图的对比。你看这个第三个金矿里面的话，它是一个相对正常的，就是第一个图，而第一个里面就发现这个它的这种这个破裂，这种小气泡破裂的这种频率特别高。如果仔细看的话，会发现表面会有很多这种超 pyrite， 就是这种黄铜矿或者是金的这种出水性特别高的这种矿物，它是破裂的，然后会影响到这个泡沫的稳定性。
So how does the particle hydrophobicity cause that sort of reaction to happen? How does it burst the bubbles like that? Well, so you can see that's the bubble there. This is the liquid film between the bubbles. So bubble, water, and bubble at the bottom there. The difference between these two particles is that this one has a moderate hydrophobicity. You can see how it sits in the water. There's its contact angle there. It has a moderate hydrophobicity. This particle has a very high hydrophobicity. Most of it sticks into the bubble, and there's its contact angle there. It has a very large contact angle.
这里就是讲两个矿物颗粒，大家看第一个矿物颗粒呢，它的表面润湿性是中等的，不算太高，所以它就是上面那一小半是在这个泡沫里，底下大部分是在外面，然后这个它的接触角是相对小的。而那边右边这颗矿物颗粒呢，它的表面润湿性相对要大很多，它的大部分是在气泡里面，只有少量的是在这个气泡的表面。就是这个泡沫的表面，大部分已经到泡沫里面，气泡那一部分。
So if this is the equilibrium contact angle over here, in order for this contact angle to reach equilibrium, water must flow out of this film, and there you see that those two contact angles are now the same.
这里就是为了讲这个水对这个颗粒的作用，就是说为了保持这个颗粒的平衡呢，它这个接触角小，跟它的反方向那边那个接触角呢，就跟它是对应的，所以这个为了保持平衡呢，水就会往出走，把那个角度呢，把这边这个角跟那边那个角是那个接触角的度数一样，保持它平衡。你看这个距离就是这个两条直线的距离会变窄，就表示水变少了，往出走，那这个颗粒变平衡了。
So in this example, if that's the equilibrium contact angle there, in order for this one to reach equilibrium, the water must flow out, and it can't reach equilibrium. All the water flows out, the films come together, and the bubble bursts. And that's why something with a large contact angle can burst bubbles like that.
而右边这个图呢，就是说，它本身这个颗粒大部分是在气泡里，在它的边缘这个水膜里面的水本来就比较少，但是它接触角比较大，为了保持这个颗粒的平衡呢，这个比较少的这个水膜里面的水还要跑掉一部分，来维持它的接触角跟它这个在气泡里面的接触角一样，让这个颗粒平衡，所以大部分水几乎是所有的水都出去了。这样的话，它这个相对平衡，但是所有的水出去之后产生一个问题，就是气泡破裂了，然后就它就是产生了图里面，就是金矿槽里第一个图那样的，就是很容易破裂这样一个问题，就是越输水越容易破裂这个问题。
Right, so that was all about hydrophobicity and how hydrophobicity can affect the frost stability. Now what about size? So this also comes from data from our lab. And this is the frost stability as a function of the feed particle size. And you can see that as the particle size becomes smaller, so the frost stability increases. So smaller particle sizes make more stable frosts. It also depends on, these are two different types of ores. So what is it about ore types that differ? It's mostly the hydrophobicity of the particles. So that's what makes the difference in the frost stability there. Also the amount of particles that are going into the froth. This is an iron ore, and so there'll be more particles in the froth, that's why it's more stable. This is a platinum ore, less particles going into the froth, that's why it's less stable. But most importantly, frost stability increases with decreasing particle size.
这里主要讲的是颗粒的大小对泡沫稳定性的影响。整体这几条线的趋势呢，就是说随着颗粒越来越小，泡沫的稳定性是越来越好的。另外就是说，我们看到用不同种类的矿，它对这个泡沫稳定性影响也不一样。比如说，也就是说矿的种类也会影响到这个泡沫的稳定性。当然，这个矿的种类主要还是由它这个固体表面的润湿性决定的。
And there's lots happening on this slide, but what I want to show is that the frost stability increases as the surface area of the particles in the concentrate increases. So that can be to do with size. So the surface area will increase as the particle size gets smaller, but it's also about the amount of particles that you're putting into the froth. So the combination of size and amount of particles that you're putting into the froth contributes eventually to the froth stability.
这里主要讲的是这个矿物的表面积对泡沫稳定性的影响，就是说泡沫稳定性越高的话，它那个这个矿物表面积在这个就是露在外面的矿物表面积其实应该是越大的，就像我们前面说的那个图一样，就是那个黑色颗粒的那个图，它应该是大部分露在这个外面的，它这样是相对是越稳定的。
So why have I been going on about froth stability? Why do we care about froth stability? Well, you can see here that if you plot recovery as a function of froth stability, this is overall recovery. Your recovery increases as your froth stability increases. So the overall recovery is highly dependent on your froth stability. You can see there for copper, nickel, PGM ores, all the recoveries increase, and this is showing you the same thing here, an increase in recovery with an increase in your froth stability.
另外，这个泡沫的稳定性其实也是跟回收率直接相关的，也就是说，你的泡沫越稳定，回收率是越高的。不管是对金矿、铜矿，还有这个铂金属矿都是一样的，还有镍矿都是，规律都是完全一样的。
Now we're going to talk a little bit about froth recovery. What is froth recovery? It's the amount of species entering the froth phase attached to air bubbles that are eventually recovered to the concentrate. And we're going to be using this equation here, the Amara P9 model of flotation, which says that the rate constant is equal to P, which is an all floatability, SB, hydrodynamic parameter, and the froth recovery.
这里是主要讲的一个泡沫的回收率。泡沫的回收率呢，就是说这个进入泡沫的这部分的就是完全进入泡沫的这部分的物质，然后它的一个跟气泡之间的一个沾到气泡上的一个回收的东西。它是包括这个进入泡沫的这部分的东西。
P is the all floatability,
and
SB is a hydrodynamic, so airflow rates and stuff like that, and then RF is the froth recovery.
它是第一部分就是完全进入可无性的东西，完全进入泡沫的那部分。另外一个就是充气，就是跟气体有关的。最后一个就是说它整体的一个泡沫的回收的 F， 是 RF。
So this is demonstrating froth recovery in this diagram here. So you can see that the froth recovery is the concentrate, the amount of valuable particles that you are recovering, divided by those that went into the froth zone as attached particles on bubbles. In that you also, so not everything that went into the froth attached to bubbles actually makes it into the concentrate. Some of it drops back. Bubbles burst and some of the particles drop back. You have entrainment happening, but that's not part of the froth recovery. Entrainment is something separate.
这里讲的就是说，所有进入泡沫的物质，它不是说完全撞到气泡上，然后被被回收了。有一部分它可能是清水的，然后就又下去了；有一部分可能是因为气泡破裂了或者怎么地，也没有站到气泡上被回收。
So if we look at this diagram, and you separate your flotation cell into a collection zone and a froth zone. So you have if you're feeding X number of valuable mineral particles into your cell, you have a recovery in the collection zone of those particles. Then the recovery to your concentrate is the recovery from the collection zone multiplied by the recovery from the froth zone. You also have some drop back into the collection zone, and what you recover in the tailings is what you did not recover in the collection zone.
这里就是讲这个，你如果正常给料的话，把这个浮选槽分为两部分，一部分就是就是回收的那种泡沫的那部分的区域，另外一部分就是煤矿的区域。那么泡沫里面被回收的那部分呢，叫concentrate里面的 C， 然后就是它就是说乘上之前那个乘上where is F where F comes from。
F is the recovery from the froth zone. So
it's a product of your overall recovery is a product of what you recovered in the pulp zone and what you recovered in the froth zone.
就是它这个就是说你这个在金矿里面的那部分，然后乘以它的这个就是整个的泡沫的，然后再加上那部分股分量 X， 就是上层的这个 冰矿的这部分的回收率。
The main point of this whole slide is that once you've worked this out, you can get an overall recovery in terms of a collection zone recovery and a froth zone recovery. And that's why we want to look at that. And we're taking that equation that we got there, an overall recovery in terms of a collection and froth zone recovery. And if you plot that, you can see that, say you get about 80% recovery in your collection zone, but you only get about 20% recovery in the froth zone, your overall recovery is less than 40%. So this is to demonstrate to you how important the froth zone is in overall flotation recovery. And in PGM ores particularly, they're not very stable. There's not a lot of valuable minerals stabilizing them. You can have froth recoveries way below 20%. And that has a big effect on your overall recovery.
这里就是一个整体的回收率。如果说你这个就是上层的它是一个就是这个有用矿物的回收率和整个泡沫的回收率，假如说你进入这个 collection row 的这部分的矿物，它总共只占了80%，然后这个泡沫里面真正回收的又只占了20%，那你整体回收的就特别少。
So we've been speaking about froth recovery, and so how do we measure froth recovery? Have any of you ever measured froth recovery in the laboratory?
这里就是讲如何在实验室计算这个泡沫的回收率。大家有没有什么你们认为应该怎么计算，或者是怎么计算更好一点？
Okay. So the way that we measure froth recovery in the laboratory is by varying the froth depth. So we'll have a flotation cell, whatever kind of flotation cell it may be. It can be a batch cell, but that's not really ideal. One of those other kinds of cells that I showed you where you can get a nice deep froth. And you do a batch flotation test at different froth heights. So you'll work out the flotation rate constant at, let's say, 3 different froth heights, and you will get a straight line relationship that looks like that.
这里讲一个泡沫的这个高度或者深度对浮选速率常数的影响，就是说泡沫越高或者越深，它的浮选速率常数是越低的，反而泡沫泡沫层越薄的话，它那个浮选速率就会靠近越薄的话，它的浮选速率常数反而越高。
When your froth depth is 0, you've only got a pulp zone, and therefore your rate constant is equal to your collection zone rate constant. When you've got a froth depth that reaches a certain point, you have no overflow anymore, so your rate constant is 0.
这里就是讲，当你的泡沫层越来越薄，当它薄到0的时候，也就是说你的整个这个就是你这个区域都算是你的这个就是那个 collection， 就是你该收进去的几乎就是那部分的话，因为它越来越薄，就完全是算到你收进去那部分，所以它的那个浮选速率常数是越来越高的。当你的泡沫越来越厚到顶部的时候，它的这个可能是因为
It is because of the which one?
It is because of the yes.
So you have it's not overflowing anymore. It's too deep. You've got a very, very deep froth.
Yeah.
It's no longer overflowing, and therefore you've got no recovery.
就是说，它顶部那部分其实流动性非常小，就是越来越高、越来越深的部分，顶部那部分是流动性非常非常小，或者几乎都不动了。那你这个回收率也是接近0。
So we
速率接近0。
So where we get to in the end is that your froth recovery, if you want to measure froth recovery at this froth height, all you do is you take the rate constant at that froth height and divide it by your collection zone rate constant, which you get by extrapolating that line to there. And the reason there's the derivation, that's why the froth recovery is equal to that. Okay. So if you want to find your froth recovery at that froth depth, all you do is you divide the rate constant at that froth depth by the pulp zone rate constant.
如果你想算中间这一部分的这个浮潜速率常数的话，那你就把这个整个的这个就是框架里面的这部分这个浮潜速率常数，然后除以它这个泡沫层的，就是你该就是收体区域，就是说金矿收体区域的这部分的速率常数，就是得到它们部分的回收率。
I can see some puzzled looks. If anyone wants to know afterwards how to do this, they can speak to me. There are other ways of measuring froth recovery, which I'm not really going to go into. I've never used them myself, and Kimrangi, who you know, she says that none of them really work very effectively. We don't really have a very effective way to measure froth recovery on site.
就是讲其实没有一个非常好、非常准确的仪器来检测这种泡沫的回收率，在整个这个浮潜就实际的这个浮潜过程中。
So we've been speaking all about froth stability and how recovery increases when you have a more stable froth. So now we think, well, we must have a very stable froth, and that's a good thing. But what about entrainment? So if you have, so just to recap quickly on the mechanisms of entrainment. Entrainment it goes with the water. Particles, non-selective, goes with the water, and it goes in that film around the water there. When you have a more stable froth, it will carry more water. You will have a bigger film around there. Therefore, a more stable froth means more entrainment, which means a lower grain.
这里就是讲一个夹带的问题。我们之前说这个气泡的这个气泡表面有一层比较薄的这种水膜，如果这个水膜越来越厚的话，它就很容易把这个其他的矿物颗粒夹到这个，比如说那个中间是一个三个气泡中间的那个边界层里面的水里面，通过这个方式夹带上去，尤其是对小颗粒来说。
So we've done a lot of froth characterization in our laboratory, and I think I've shown you these before, but we use big long columns, tall columns, about 2 meter flotation column in order to develop big deep froths. This is where we can measure froth recovery. We've got froth zones of different froth heights. We've got the hybrid flotation cell, which if you were here on the first day, I showed you the hybrid flotation cell. It's a mechanical device at the bottom with a large froth zone on the top. We have this froth characterization column, very simple. You just measure the froth rise rate and the maximum height that it attains. And this is basically the same thing, just at full scale, in a full scale flotation cell.
这里是他们实验室设计的关于这个来表征这种泡沫性质的不同的浮潜柱。比如说第一个就是这种比较高、比较细的这种浮潜柱，大概有2米高吧。他们就是说这个柱子通常比较细，跟这个泡沫进入到里面的话，它这个高度比较高，可以看到它2米有多高，或者说收集的这个泡沫就可以拉开这个层距，然后也相对高一点，不像我们比如说平时薄薄一层也看不出它到底有什么区别。还有就是后面这种就是通过这个 我们收集的泡沫呢，就是通过不同的这种高中低这种三种不同的装置来分辨它到底是有能收集多少。另外还有是，比如第三个就是他们自己设计的这种就是我们通常说的那种贝克曼的那种装置，就是来测泡沫稳定性的这种装置，就是说你通过这个绿色的泵把气泵进去之后，这个泡沫上来之后，你算这个泡沫在泡沫的高度随着时间下降的这么一个过程来计算泡沫的稳定性，还有后面这种机械的这种浮选柱，还有就是说这种模仿这个工业上的完全这种 full scale 的这种浮选柱。
Here's just some more pictures of us on site. We do a lot of site work, and the whole objective of all of this froth work is to be able to use this data on site in order to predict what, if you know froth stabilities, to be able to predict things like mass pull, recoveries, grades. So you can see here some of my colleagues. There's our big column cell, another of my colleagues. You can see the froth. We're using smaller cells here. We take samples from the flotation cell, directly from the flotation cell, to float them straight away. And then me with my big flotation column.
这里就是他们在浮选现场，在选矿现场的用他们自制的这些浮选柱对选矿现场的一些矿浆或者是这种现场采样进行浮选和试验。
Okay, so if we want to do research at full scale, then we need lab scale devices that can be scalable, and these are the sorts of things. So what we want to do is be able to do experiments in the laboratory that will predict what is going to happen on site. And these are some of the parameters that if they change in the laboratory, they're going to change what happens at full scale.
这里就是讲，就是说，在实验过程中做实验的，在实验室做实验的时候，可能你就会要考虑，比如说这个影响这种泡沫稳定性的因素是哪几个？比如说气泡的大小、气泡的容量，还有这种就是说有单位体积的这种泡沫里到底有多少固体？另外就是这种夹带，因为这些因素也会影响到现场的整个操作，或者说它整个这个效果就完全不一样。
So this is a very simple test that we want to use to be able to predict what's going on, to be able to predict froth stability at full scale. So this is I've showed you this before. This is our froth stability device. And if you measure the froth height as a function of time, it looks something like that. And you can fit a little empirical equation to it. Mostly we're interested in this number over here, the maximum froth height divided by the airflow rate, the superficial gas velocity, gives you the froth stability.
这里是计算泡沫稳定性的一个过程，就是前面讲的这个装置，就是通过这个绿色的泵充气之后，它这个泡沫的高度随着时间的变化，就得到右边这样一个曲线。但是这个它泡沫的高度不是说一直上升的，当它上升到一定高度，它可能就不动了。这个最大的高度除以它这个通气的速率，就得到了动态的泡沫稳定性，就是最下面这个公式。
This is just showing you a picture of how we do it on site, a video. So we've got the column going down into the pulp zone, and you can see how the froth grows up the column. And so basically, that height that the froth can attain, that's your froth potential. And you can imagine if that's the height that it could attain, if that's what the potential that it has, that's its potential for flow. If you can only attain a froth height like this, the flow is going to be small. if you can attain a froth height up here, your flow is going to be big. And so this is the idea behind being able to, if you can measure the froth stability, you can predict the mass flow.
就是通过这种泡沫稳定性的测量，可以对整个框架这种流动性做一个表征。比如说它这个图里面这个泡是逐渐上升的，可以上升到非常相对来说非常高的一个高度。那如果说它上升的高度可能只有一点点的话，说明它整个这个泡沫的流动性也是不怎么好的。
So we've done some work on scale up, and so basically if we do this measurement in the laboratory, how are we going to scale it up to full scale? Well, one of it is as a function of the column diameter that you use. Does that affect your froth stability? And the answer is yes. So here's your different column diameters, and this is the measured froth stability. And the froth stability, actually, the apparent froth stability increases as that column diameter increases. And so this, where it starts to plateau out here, is where the true full-scale froth stability is at infinite column diameter.
这里就是讲这个他们自制的这种浮选柱，在实际的过程中，是不是它的浮选柱这个直径的大小会不会影响它这个所测量这种泡沫的稳定性的结果？实际上是表明说，这个浮选柱这个直径越大的话，它的这个上升的这个同样的泡沫进去以后上升的高度是越高的，表明它的泡沫的稳定性相对来说是越高的。
What about bubble size? And I'm talking about your starting bubble size in the pulp. So if this is your bubble size here, then as your bubble size increases, so your froth stability decreases. So your measured froth stability is also very dependent on your pulp bubble size.
就是说这个泡沫的稳定性也与泡沫中这种气泡的大小有关系。当这个气泡越来越大的话，稳定性也是相对来说越来越差。
So what the whole idea is to be able to do a routine or an online froth stability test like this, a small scale test, which you can scale up to full scale, and then if you plot your froth stability versus your mass pull, we've done work in the lab where there is let me start here. So remember I told you that you have this froth potential, and the greater your froth stability, the more the potential for flow. Here you have the greater your froth stability, the more the potential for flow. That's your mass pull over there. You know what I mean by mass pull, your mass flow. And so yeah, we've demonstrated this is for different ores. It doesn't matter what kind of ore you use, it doesn't matter what reagents you use. If you can measure froth stability, you can predict a mass pull, and that's the whole idea behind this work.
就是说，通过对泡沫稳定性的测量，你可以对整个这个选矿的这个整体的这个泡沫里面的一个做一个预测，就是说你这个你上层有多少泡，就是上层泡沫有多少，或者说它们怎么样，对，进行一个预测。比如说它稳定性几乎这个规律，不管是对铜矿、镍矿还是其他矿都差不多，就是说这个稳定性越高的话，它这个就是上层就是实际矿场上上层那种矿的可操作性是越大的，或者说它这个矿这个程度是越好的。 而且这部分是基本上也是由电位决定的。你这个泡沫稳定性越高，说明这个电位相对来说相对高一些，然后这个上层这个泡沫里面可操控的这部分矿越多。
Here's showing some of the frostability and mass pull down a rougher bank. So this is full-scale frostability that we measured. Frostability, that's the rougher bank there. You can see this nice smooth decay down the bank. So you have high frostability at the top of the bank in the first cell. You have much lower frostability in the last cell in the bank. Why? It's all about the amount and the type of particles that you're putting into your froth. In the first cell, you've got lots of floatable stuff of moderate, good hydrophobicity, whereas down here you haven't got so much floatable stuff left, so you have a lower frostability.
这个就是通过对这个金矿不同金矿槽里的这个泡沫的稳定性的测量，发现是最先的那个第一个它的泡沫稳定性是最好的，随着金矿槽越来越往后的话，它那个稳定性是越来越不好的，就像我们做浮选一样，第一次刮泡基本上是最好的，后面可能越来越少，或者是越来越相对是不好的。
But we took that frostability here and we plotted it versus the solids flow, and that's the relationship. So again, demonstrating that the solids flow is a function of the frostability.
也就是说，这个泡沫里面这个这个固体的流动性也是跟泡沫的稳定性有一定关系的。泡沫的稳定性越高的话，说明这个泡沫层里面固体的流动性也是越好的。
This is just the same as what I've shown you before, so I'm going to go over that. And this is just our summary. So I think we've shown you need to manage your froth well on site in order to have an efficient and a good flotation performance. Froth recovery, there are some measurement techniques, but the way we do it is we usually model fit it. And yeah, our research is ongoing, and we are working on being able to have a predictive measure of mass pull recovery and grain.
这里就是讲这个这一节课的小节，就是首先说这个泡沫的稳定性对浮选，泡沫的性能对浮选是对浮选的一个直接的反馈。泡沫的稳定性，以它这个就他们测量的这种浮选区里面泡沫的稳定性，可以直接反映它就是实际浮选里面的这种 mass pull 整个这个矿物的流动性怎么样。另外就是说，他们通过模拟和实验都能预测出这个实际矿场中选矿这个系统的好坏。
Okay, thanks. Are there any questions on this?
I just want to make a comment for the students that I think this talk has shown so important to link the laboratory work to plant work, because otherwise the relevance of the laboratory work is limited. And I think what Belinda herself does so well, spends a lot of her life on plants. You see the pictures put there, and that's critically important. And I think our group in Cape Town, if I may say so myself, is quite strong. The JK used to be very strong in doing that. I think it's lost a little bit. But we work closely with the JK. But the importance of doing plant work for people doing linking the laboratory work to plant work, I think what Belinda has shown so well. Thank you.
Connor 教授这里强调就是说，你实验室的结果跟现场的结果一定要对应或者匹配，或者说你一定要关注这个，就是说你不能说光做实验，然后做完了就关注现场这个，一定要把自己的实验跟现场紧密的联系在一起。
You agree? I have a question. There was a slide you showed where you set possibility to get surface area.
Yes.
But the unit there was square meter. So you need total surface area of all the particles, not square meter per gram.
No.
So how do you calculate that?
The amount of particles that you get in the concentrate multiplied by their specific surface
So
area.
you do a BET.
Yeah.
But the thing about that is that if you've got few particles or large, few small particles,
Yes.
this is many large particles, you have the same.
Exactly.
You think that would work out to be the same?
It does. It really does. That's what Martin's idea again.
It's counterintuitive.
You have few small particles.
It ignores the size, particle size, surface area, which is different.
Yes. Yes. You have few small particles or more large particles. No.
Yeah, that's right. Well, if you have few small particles, we have the same surface area as many large particles.
Yes. Yes.
I'll ask to think of it.
That was many size fractions put together of various different.
Fascinating.
Yeah. Okay. All right. Thanks. So we start the next one at 2:30 again, right? Yes. Okay. 2:30. Thanks. Okay.
下午2点半讲浮选电化学，由这个 O'Connor 教授里面浮选电化学在国际基础里面的一些机理现象和问题。
Where's that computer? Where is it?
Just have a
You need to have a meeting with Neil Park.
Oh, yeah.
So I think he's going to arrange something.
Yeah, you're right.
Belinda, you got a question?
Oh.